Previously, I talked about the alternating series error bound and kind of intuitively the idea behind using the next unused term to give us a sense of how good our partial sum or approximation is in approximating the actual sum of a convergent alternating series. I want to start today by just reviewing this quick image here that I have to kind of give you a sense visually or maybe even numerically what's happening when we are continually adding alternating terms in a series. So first off, I want to point out that the actual sum of this alternating series is located right over here. There's our actual sum of this alternating series. Now, if the first term in our series is positive here, then we see that our first term, when we add the first term in our series and we say, okay, we're going to stop there and say that's my partial sum, that's my approximation. So I'm trying to approximate the actual sum of the series by adding just the first term. And I can see here clearly that this is an over approximation. Well, if that is my over approximation, then what we have here is this, the absolute value of this distance or this distance here, this would represent my R sub 1. In other words, it's the sum of the remaining terms after the first term in our series. And we can see here it's off by quite a bit. Now, if I continue to do this, now if I then add my next term in our series, if I add, in this case, negative b2, because it's an alternating series, so my next term is negative. So if I then add this negative term, now my partial sum is right over here. This is S sub 2. So now we see that our approximation here, this is an under approximation because now my R sub 2, which is this distance over here, my R sub 2 is lower, is less than the actual sum of our series. So now we have an under approximation. And this is going to continue on, right? If I then stop with my third partial sum, or the sum of the first three terms, now I'm back to being an over approximation. Then if I add the next term, which is negative, I'm back to being an under approximation, and so on and so forth. And you can kind of start to see here after a while that, let me just go ahead and erase this so we don't get too mixed up. So after a while, let's say I'm right over here now. Now I see that S sub 6 is an under approximation, and my remainder has now decreased, right? So my remainder, or another way of thinking about the remainder, as I said before, is thinking of it as an error. How much are we off by? And we see here that it's definitely smaller than it once was. And we're going to just keep on doing this over and over again. And the idea is that as we keep on doing this, the more terms we add, the better and better of an approximation we have to our actual sum. Or in other words, the more terms that you add, the closer your partial sum is going to be to your actual sum. Conversely, what's going to happen with your remainder? Your remainder is going to get smaller and smaller and smaller. It's going to approach zero, right? Now, of course, in practice, we can't ever actually add up an infinite number of terms. That's why we're even having this conversation about using partial sums to approximate the sum of a series. What I want to do in this video now is to actually just go ahead and just try a couple of practice problems, just give us a chance to work through a few problems, and then you can try a few on your own and check solutions in Google Classroom. So let's start with this first one. The first thing that we're going to do here is we're just going to show that this series converges. Now, you don't have to do this for every single one, but anytime it asks you to, obviously you want to make sure you know how to show that this series does indeed converge. So my first step is to actually write out the first however many number terms in the series. And I can see in part B, it's going to ask me for the sixth partial sum. So I definitely want to add up first, however, at least first six terms. So let's go ahead and write this. Our first term is going to be positive because we have negative 1 raised to the second power. And this is going to be 3 over 4. And just to save some time and be efficient here, I've already kind of calculated a few of these values ahead of time. So I'm just going to start writing them out, but you can just go ahead and pause on your own and calculate these. But these are the first, what we have here. So 1, 2, 3, 4, 5, the first 6 terms in our series. Okay. Now this is going to continue. I'm going to write ... in a second. The first step that I want to do is I want to show that this series converges. So the first thing I can write is I can say, look, the absolute value of 1 over 4 is less than the absolute value of 3/4. More specifically, a sub n plus 1 is less than a sub n. And you can do this also by using the derivative to show that the derivative is negative. You could also just plug in n into our a sub n rule and show that algebraically a sub n plus 1 must be less than a sub n. But this works as well, as long as we indicate that a sub n plus 1 is indeed less than a sub n. Next, I'm now going to show that the limit of a sub n as n approaches infinity, and actually let's write it out. This is 3 over 2 to the n times n plus 1. Well, our numerator here is bounded. It's a finite value. It's just a constant, but we're dividing by a denominator that's going to approach infinity, which means this is equal to 0. Therefore, we can say that this series converges by the alternating series test. Okay, so part A is done there. Now part B, I'm going to go ahead and I'm going to calculate what S sub 6 is. So part B here is, again, S sub 6 is the sum of all of these, the first 6 terms in our series. So we're just going to add them up. And so for the sake of time, I'm going to tell you that this comes out to approximately 0.5651, and let's round to that 5th decimal spot. So this is going to be approximately this value. Now, we want to show, the next part of this is to show that this partial sum, right, this partial sum which is approximating our actual sum, we want to show that it differs from the actual sum by less than 0.003. Well, how do we do that? We employ the alternating series error bound theorem, which says in a convergent alternating series, our partial sum is going to be off by the actual sum by no more, in fact, it's less than or equal to our next unused term. So what is our next unused term? This would be the first term we're not adding. In other words, it's our 7th term, right? This is our next unused term, which is, well, if we go back to our series here, let's figure out what the next unused term would be. This would be 3 over 2 to the 7th times 7 plus 1, which comes out to 1024. And we see that this is approximately equal to 0.0029, and that just squeezes right under 0.003. So we can see that our partial sum is going to be differing from the actual sum of the series by 0.0029. This represents our error. This is how much we are off by. And we've shown that that error is indeed less than 0.003. Now, just as an exercise here, and this isn't part of the directions or is not required, but I think it's a good thinking exercise here, is to ask ourselves, okay, so is this partial sum here, is this an under approximation or an over approximation of what the actual sum of our series is? Well, let's think about this. We know that our actual sum is pretty darn close to this value. It's really close to this partial sum that we've calculated. In fact, it's going to be close by what we saw as 0.0029. That's how much it's off by. But let's think about then. So our first term here was 3/4, or approximately 0.75. This is clearly an over approximation, and this is going back to this image that I had here for us to think about. So we have an over approximation here. Now, when we add the second term, 0.75 minus 0.25, now we have an under approximation. And we know the actual sum is really close to 0.56. So we can kind of repeat this. All right, over here, this is under. When I add the first 5 terms in our series, we're back to having an over approximation. And you could just pause and try this bit by bit. Add one of these every single time. And you can see it kind of oscillate back and forth between being an over and an under approximation. So what we then say is, now if we go ahead and subtract 3 over 448, we now see we have an under approximation, right? In other words, we can say that this partial sum that we found, S sub 6, we know it's less than or equal to the actual sum of our series. This is an under approximation, right? But we know, even though this partial sum is less than or equal to the sum, we know that this sum can't go beyond this amount, right? So if you take 0.56518 and add this error that we have, 0.0029, we're saying that our actual sum must be less than or equal to that number. And it's got to actually be less than that, because we saw in practice that if we have a partial sum, then our remaining terms in this case will actually add up to something that's less than 3 over 1024. But this gives you a good sense of kind of mathematically thinking about whether or not this would be an over or under approximation. Let me go ahead and try one more problem now. We'll try number 2, which is a bit of a shorter problem. So let's look at this one. So this one here says, given this series, let's approximate the sum using the first 5 terms. So in part A, I don't have to show that it converges here. It's not part of what was asked. So I'm just going to say, all right, my sum is approximately equal to my 5th partial sum. Okay, and I just want to make sure I did something right up there. Okay, my 5th partial sum, which is the sum of the following. 1, and the next term would be 2, plus 1 over 3 factorial, minus 1 over 4 factorial, plus 1 over 5 factorial, and so on. Oh, actually, not so on. It's a partial sum. Sorry about that. Now, if I add up all those terms, I get approximately 0.63 repeating. So there is our approximation, right? We're saying our sum is going to be really close to this number. Well, let's figure out what's the largest possible error that we could have. Our alternating series error here must be less than or equal to the absolute value of our next unused term, which would be 1 over, what's the next unused term? 6 factorial. This is our next unused term. And how much is it off by? What is that numerically? It's approximately 0.00139, right? So that's the largest possible error that we could have in this alternating series. So I encourage you now to try the problems on the back and go ahead and check your solutions in Google Classroom. And hopefully this helped.